Hi, everyone. Hello. Good afternoon. I'm sorry for my voice. I have lost my voice at the booth. I can't find it. All right. So thank you all of you to join the call, this talk. I'm very happy to see everyone here. Uh, just to get some understanding, how many of you have visited us at the booth? Oh, most of you. Okay, awesome. So the ones who haven't, you're more than welcome to join our booth. We can talk more. We can show some live demonstrations as well. Is the audio fine at the end? Yeah? Okay, awesome. So, yeah, I will just get right into the talk. Build computing in the real world. This has been something that we have been doing since the last close to 3 years on my own side. We actually have a team of around 12 people back in India. We've been trying to figure out why building in the real world is tougher than building in the cloud. Right? Most of you have seen, right, like in the last 15, 20 years, the way we build applications on the cloud has just changed, right? And the barrier keeps going lower and lower, right? You have Herokus, you have all sorts of applications today where you just run a command line, like a command on your prompt, and the application gets deployed, right? But why are we so behind on the hardware? Why is it still intimidating? Why it takes time? Why the life cycles are longer? And that's the question we start asking. So we're going to explore how the journey with building Mecha has been. The takeaways would, like, I'm sure there will be different takeaways for a lot of folks here, right? People who want to enter into hardware. How many of you are keen to get into hardware? Okay, nice. How many of you come from a software background and haven't done hardware? Me included. Okay. In fact, I did software for most of my professional life. I ran a tech consulting for 10 years, did all sorts of projects, worked in various sectors, and I think one of the execution is when the entire background for Mecha started. I did my bachelor's in computer science back in 2014. I have been an engineer all my life. I just like building things, and it could be hardware, it could be software, right? So it has always been something that I would like to keep doing. Yeah, cool. We'll just wait for them to settle down. Okay, cool. Yeah, so let's try and answer the question. Building hardware is hard, right? The word hard is already in the word hardware. So when we look at a typical hardware project, it usually runs through these steps, each requiring specialized engineering skills and its own inter and intra-process dependencies. So typically, you're going to start with system on chip, right? You're going to decide on your SoC, right? This remains the fundamental decision before you start building any hardware. For people not familiar with the system on chip, so system on chip is your chipset, right? Like think of it like earlier we used to call it just the processor, but now they are systems because you will have a GPU component to it. You would have a video and a video encoder, decoder, GPU, ALU, maybe an NPU, right? All of those combined into one single, even a crypto layer, right? Like a crypto accelerator. So all of those combine into a single chipset, and that would become your system on chip. So you choose the right system on chip. You maybe start with the system on module, so you don't have to worry about building the processor on your PCB, right? The processor is a very tricky beast to handle because a typical modern day microprocessor is going to have around 200 to 1,000 pins, right? So when you build your PCB board, you want to program around, or you want to have the schematics ready for 1,000 pins, right? Imagine the complexity towards it. So they end up usually starting with a system on module, and then you start doing a PCB design. So your hardware designers are going to design your PCB. Your embed engineers are going to start preparing your board support package. So board support package is nothing but when you bring your peripherals on your PCB, you need to get your, let's say if you're going to build in Linux kernel, so you're going to get your device tree ready, you're going to get all your drivers sorted, you're going to have the interfacing done with the Linux kernel, so that would be part of your board support package. And then you're going to have an image generation. The image generation would be like a rootfs and an application layer combined with your kernel that you will end up flashing on your device. In parallel to that, you will have your software engineers setting up the tool chain, building applications, maybe doing cloud integrations, things like provisioning, remote updates, and diagnostics, right? So yeah, I mean, if you look at the overall chart, you understand that there is not a job for a single person. You need an entire, like an orchestra of people working together and identifying blockers. Like the hardware guy is going to tell you that, okay, it's a software issue. The software guy is going to tell you it's the hardware issue. Right? I have been stuck in this loop multiple times. Yeah. So with respect to Mecha, we refer to ourselves as the framework for hardware. Right, not to be confused with the laptop guys, but we really love them. Yeah. So the idea is you start with a bare, like already a set hardware, right? That is good enough for you to get started with. Build the extension, build your application, install our cloud agent, integrate APIs and pipelines, right? So I'm going to come to the cloud layer also, but yeah, that's how we see the Mecha layer working. Now, just from an origin point of view, this started early in 2020. We were doing a digitalization project for Siemens. You can actually see me on the chair down below, trying to figure it out. We are doing all the wiring in Siemens Control Lab. We are trying to set up a streaming solution. On the right side, you can see a video wall which is showing all the different control systems that were available in the control room. So we basically worked for their transformers factory, right? So we tried to automate their transformer testing processes, right, and give like a cloud or a remote portal for their auditors and their inspectors to verify the testing done on these power transformers. And you know what? We all do software, it's all nice and it all runs on your laptop, but when you see like a 20-meter power transformer, right, there's a lot more respect towards engineering. Yeah, on the right, on the lower right, you can see a contraption. In fact, that contraption was our 3D printed Raspberry Pi, right? We started with a Pi, then the customer said, okay, this is not going to work for us, please put a battery inside. Okay, we'll put a battery inside. Okay, but how do I know how much battery is left? Okay, we will do one thing. We'll open up a power bank with a battery indicator. We will remove the PCB, we'll remove the battery, we'll put it inside a 3D print housing, and we will give it to you. Then like, okay, how do I know if the application is running or not? How do I diagnose it? Right, how are you going to support to me? Right, so these questions started coming, and then we started realizing, why is this so hard? To be honest, we just had 2 Python scripts. We just had to create those as systemctl services and just have them start on reboot. Right, that was the only thing we had to do, right? And I mean, to all your Linux administrators, that would be something that you would do for breakfast on your virtual machines. Yeah? Yeah, most of the project actually deployed at Siemens continues, but in a limited capacity. Happy to give them Mecha now. Yeah, so in 2022, we jumped the rabbit hole. We thought, okay, why can't hardware be easier? We started understanding the challenges in the hardware industry, and me being from a software background, it gave us a very different perspective than embedded engineers, right? Embedded engineers, they still have like a very linear way of thinking on the approach. They're like, okay, we are very process oriented, we'll go on each of these steps and then we will execute, right? So we had that, the advantage of, you can say, a third perspective, and we used that. And the idea was, let's do a unified approach. We'll build our hardware, we'll build our software on the device, and we'll also build our cloud, right? This gives us a unique advantage, because you see a lot of hardware people making hardware, but they don't make up software. You see cloud services building good cloud services, but they don't end up supporting hardware. So there's always an uphill battle going between the two. Yeah, and the focus has been like, let's build a computing stack for applications in the physical world for everyone. I mean, the everyone part is important to us. We don't want to make it enterprise only. People in enterprise, they know how slow the sales can get, right? It can suck the living life out of you, but yeah. Okay, so now getting to designing the hardware. We started conceptualizing in 2021. We started with a simple box. It was 250 cross 250 mm, almost more than an inch thick. We started placing basic components, and yeah, we kept improving the design. So the idea was, let's do the concept design first before we even jump into the mechanical design. So we kept improving the form, and overall, like you can see the gradual process on how it slowly converted into the Comet that you see today at our booth. Yeah, I think most of you have already seen the Comet device. While we are doing this, we also created the engineering validation test prototype. Right, you can see the first PCBs in our hand. We actually had to visit the SMT factory. We stood in the SMT factory ensuring that all the components get soldered correctly. We ourselves ended up doing the automatic optical inspection as well. And you can see the first 3D printed device on the bottom right, which houses the early Comet board. While we were doing this, we also ended up building the entire software layer. I mean, I've done Linux earlier, right? Like working on as your own home computer, but building Linux out, right? Like generating the images out, working on the kernel, that has been new, and that is how we started getting into this as well. One of the parts that I think I earned a lot of respect is that we take so many things granted as application developers, right? So when we open up a Chrome browser or when we open up any application, right, we really don't understand the layers and layers of software stack that is enabling that, right? Like if you're into Linux, then you would understand that there is something like a display rendering manager, you have something like Valent and X11, you have a compositor layer, your application is talking to the compositor, right? You need to ensure your protocols are met. There is so much of stuff going around, right? And while doing that, we actually picked up Rust. So most of our software stack is in Rust. We ended up writing our own GUI. We have open sourced it. I'll be sharing the repository links later. But yeah, we wrote the entire Valent shell. It's similar to something the guys at System 76 are also doing with their Cosmic desktop, but we are focused more on small touchscreen interfaces, right? And yeah, I mean, you already have iOS and Android, right? And I think Linux deserves its own operating system UI as well. Thank you. Yeah, and then the Comet arrives. This is our final iteration. I think it has been around 4 iterations before we got here, and we're now slowly moving into production. We developed the extension system. In fact, today, for the first time, we have an operating, like a working extension on our booth. So yeah, please drop in. Yeah, just to clear up specs very quickly, you have dual band Wi-Fi, a quad-core processor, 4 GB RAM, there's a battery on board, eMMC, there's a crypto secure element, so you can use it for your cryptography. There are 40 Pogo pins also available, which is the extension system. You have an RTC on board, so you basically can use it in a remote deployment where you may not have reliable internet all the time, and you want to ensure that like even something like time is something that we take granted on our laptops, right? Like without a RTC on your machines, right, it is going to forget time, right? Yeah, it's going to forget time as long as it doesn't connect to the internet, right? So yeah, so there's an RTC also on board, and yeah, this is the overall PCB architecture that we developed. The firmware, it's running the U-boot bootloader 2304. Bootloaders tend to not get upgraded quickly because they are the foundation of, like, they are the layer that happens before your kernel. So the boot cycle on a hardware is also very tricky. You normally have a software that is already in your system on chip, SoC, which is like the primary loader, which is going to call a secondary program loader, which will then start your bootloader, and then the bootloader starts your kernel, right? It's a weird game that happens, right? Like one program starts, it loads up another program on the register, and then it keeps passing around, right, till your kernel starts booting up. The distro is based on Debian 12, so anything that would work on Debian would work out of the box. There's a GPU-powered shell, cross-platform SDKs using gRPCs, build tools for the bootloader, the kernel, and the rootfs. And as a principle, everything on the device is fully open source software. The extensions, there are 40 such pins. All the hardware is open source, so you could print out your own extensions. Each pin corresponds to a different digital interface. Again, the PCB extensions that we build, we guarantee that they would be open source, so you could, like, in fact, I still don't know how to design a PCB. I have team members who do really good stuff, right? And I'm very keen to start learning how to design PCBs, right? Because why get limited to software? Yeah, these are just some internal sides of the extensions. You can see that you have magnets on 3 sides. This is what forms the magnetic, you can say, the attachment. We also use an alternating pattern which helps. So all of them are not north-facing or south-facing. They are alternative, so when it actually attaches, it helps in better grips. And yeah, the PCBs are very straightforward. We just solder them up on our own. We do it at our offices. Yeah. Now we have more hardware. Keep going down the rabbit hole. We built the single board computer because why not? Uh, and we want to. This is already available at our booth right now, but we want to launch it sometime later next year. There's a compute module for OEM applications. Okay, now I think this ends on the hardware side. So now we figured out hardware, right? We figured out a base hardware that you can use and build applications. And we want to promote the idea of build using the tools you already know. So if you noticed, our SDKs are all gRPC compliant. So if you love to program in any language, like one of the things that I never understood with these mobile SDK platforms, right? Your iOS and Android is, iOS will tell you use Objective-C. Okay, you don't like it now, we have Swift UI. Okay, Android will say, okay, you start with Java, okay, and then you switch to Kotlin, right? But then why should it not be polyglot, right? Like, why should we be restricted ourselves to only one language? So we want to promote you using your own language that you already know. So that is one important aspect of the SDK layer, which we want people to be able to use. And because it's Linux, you can even bypass our SDK and communicate to the hardware directly. Sorry, I skipped a slide. Okay, now let's come to the cloud. How many people work on the cloud? Okay, nice. So this is where it gets interesting. I worked on the cloud for a good amount of time, and we wanted to do something on the cloud which helps the edge, right? So the core idea was to build core services for the edge that worked in the same way as the cloud, right? Like early on, I could not really make sense that why do we, see, if you launch a virtual machine on AWS, it's still Linux, right? You have a Linux in your hand, there's a Linux there, right? Like, why do we have different ways of working on it, right? So we started with this kind of a concept, and we thought, okay, let's try to program edge the way we program on the cloud. And coincidentally, I was just reading Ask Me Anything AMA on Reddit, and Kevin Scott had the similar reply that we were already thinking about. So somebody asked him, how do you see the, just zoom in, yeah. How do you see the cloud usage in relation to edge computing 5 years? And I think the part, what I highlighted talks about that why do we see them as distinct things where you write software in fundamentally different ways depending on which environment you are in, but one continuous compute fabric that you can coordinate across to solve problems in more interesting ways than if you are confined to one or the other. Yeah, so this became a foundation of our cloud services. And yeah, in fact, we were already thinking of it, and it was nice to have Kevin Scott agree with us. Yeah, so now let's talk about deploying to production. Now you have the hardware, you're able to build applications on it, everything is nice and sunny, right? But the moment you deliver these hardware to your customers and they're going to install it, right, you're going to have real questions coming up. The questions around how do you authenticate, how do you authorize those devices, right? Like when they connect to your network unattended, right? How do you identify them, right? Because we typically, as users, as humans, we end up authorizing using our TOTPs, our passwords, and things that we remember, right? But you have an unattended hardware, right? How does it remember who it is? And how does a cloud reliably understand that, okay, this is the device that is connecting to it? The second problem comes in is the messaging part, and then you have telemetry and diagnosis. How do you collect telemetry data from your devices? People familiar with observability, right, you'd understand that you end up instrumenting your applications, you send up metrics, logs, and traces, and then you end up accumulating them in an observability platform, something like Grafana or Datadog or anything like that. Yeah. Secure networking, right? Like you may want your edge devices to be able to talk to each other, right? So how do you have a networking deployed between them, right? And you have to understand these would not be deployed in a very reliable network infrastructure which a data center would guarantee. So you need to ensure that those your services and your stack is able to manage unreliable connections. Things like remote control and access, right? What if your application stops working, right? And you need to diagnose it, right? How do you manage to do that? Yeah. And yeah, the last one is the software update. Yeah. So these are the challenges in deploying to production, right? Like part of building in the real world, right? And if you think about it, are they not similar to the problems that we have in the cloud? How many of you agree? Awesome. So authentication authorization, right? So if people working on AWS, you end up assigning like a role to your EC2 server, right? How many of you are familiar with that? Yeah. So we end up assigning a role to the EC2 server that guarantees its authentication and authorization. You have a messaging system, so you end up using something like Kinesis, or you have Kafka, right, and stuff like that. Telemetry, obviously everybody knows. You have open telemetry, other SDKs, and own platforms given by the cloud vendors. Secure networking, the first thing that we start with is we create a virtual private network, and we launch all the EC2 or all the VMs within those particular networks. So the problems are still the same. Yeah, remote control, we end up SSHing into these servers. Yeah, so that remains the same. Software update, right? So typical process is to do a Docker pull or something like that, and you get your software updated, or you could deploy using CI/CD. Yep, so yeah, the overlap still remains the same. Some of the cloud services that we manage is we provide provisioning and identity services for authentication. This could be used to auto-deploy devices on field, end-to-end encrypted messaging, right? So we basically take care of the entire certificate issuing process. So to answer the question on how the authentication of devices work, you end up issuing like the typical standard is that you issue a X509 certificate to the device. It's a signed certificate, so you should have a trusted certificate authority which signs the certificate and then delivers on the device, right? So when the device is communicating, it's going to provide the certificate to the cloud, and once the cloud verifies the certificate, it is going to accept the connection. The other part that we provide in our open source agent is the virtualized networking. So the idea is that can we have all the cloud machines and edge machine play together in a single network? So for that, the best thing that we use is WireGuard. WireGuard is a Linux subsystem, super awesome. People who have tried out something like Tailscale, right? They would understand that, okay, Tailscale is just a layer on top of WireGuard. So the idea is that your cloud and your edge could be in the same private network without physically being there, right? So we manage the whole WireGuard provisioning and the P2P networking and discovery. There's a very good concept in WireGuard called the NAT traversal, right? It's a very black magic kind of connection way to get two devices on the internet without a static IP to be able to form a connection between them, right? So typically when we talk to a server, the server ends up having a public IP that we access to, right? But if both of them do not have a public IP, right, how do we end up getting them connected, right? So it's a very good networking gimmick. I mean, out of all these 4 versions, I think I can have separate talks on each of them and dig deeper more into how each of them works. But yeah, the good thing is we're going to document all of this in your website to its core detail on how the entire architecture works. And yeah, the last thing that we do is the application gateways. So this is actually a demo. We have it. We're going to try and run it on the rover here, right? So the idea is the rover is running a service in Node.js. It's a local service, right? It runs on a port 4000. So I'm running a Node.js service on 4000. When you send a HTTP request to the service, the rover is going to move, right? Now we're going to try and use this concept, and we're going to connect this service, the local service on the device to the cloud, right? In the same concept as how a load balancer works on top of your EC2 instances, right? So when you expose a load balancer, you just end up doing a port mapping, right? Like the load balancer port would be 80 and your service port would be some other port 3000 or something like that, and you just end up mapping that. We'll try to do the same on the edge. Yeah. Yeah. Coming to open telemetry, right? What we end up doing is we integrate the entire open telemetry stack. So our Mecha agent ends up running a gRPC endpoint, which is running on the device. So if you have an application that you deploy on the field, you just end up sending your metrics and logs to the local endpoint on the device itself, right? And our messaging architecture will ensure that we will deliver the messages to Prometheus and Loki, and then make it available for you to visualize in Grafana. Right, and you could swap it out with any other observability platform. So this ends up solving your telemetry problem in the exact same way you end up building your own cloud applications. So people already using open telemetry in their applications? Yeah, it's good. Yeah, so open telemetry actually got created because the need of having standardization in telemetry, because Datadog came up with their own spec, New Relic came up with their own spec, Azure had their own spec, everybody had all their open specs, and moving between vendors was impossible. So then everybody got together in a room, figured out, okay, let's just have one spec, we will all be happy with it, and we will maintain that spec, and that's how the open telemetry came up. Yeah. So because of open telemetry, you could swap your observability backend. It doesn't have to be Grafana, it could be anything else. Yeah. Yeah, so we're just showing a simple JavaScript example of creating a collector, like a URL. You just specify your localhost agent URL, and yeah, you just set up your tracer and logs exporter, and that's it. Your application gets observable, or you can say instrumented. So we'll quickly look at a console demo. So I'm going to provision the hardware first. So I'll just say add machine. I'm going to select, okay, we haven't put the metal, but okay, I'll just assume it is Comet. And yeah, our cloud layer is agnostic of hardware, so we don't really care if you bring AWS or you bring Raspberry Pi or you bring any of your Linux machines. As long as it runs Linux, our agent will support it. So I'm just going to select Comet. And on the Comet, we actually have a GUI application for this, but for the Metal, because it doesn't have a display, I'm just going to use a gRPC endpoint to provision. So the Mecha agent has a gRPC endpoint, and my laptop is in the same Wi-Fi with the rover, so I can actually send it over the Wi-Fi. So yeah, so it says enter the code displayed on the app or the CLI. Okay. So I'm just going to generate a code. So I have a gRPC on Postman. I have a gRPC endpoint which says generate code. I don't know if it is, I'll try to zoom in a bit. Yeah, so like provisioning service generate code. And this IP corresponds to the Mecha Metal, the single board computer on the rover. I'm going to invoke it. It generates a provisioning code. I'm going to copy the provisioning code. Paste it here. It says processing request. And now I'm just going to call another endpoint on gRPC, which will start the provisioning using the same code. So what really is happening in the background is that the device is actually, like when I entered the code on the server, the server issued a small, like a 60-second token on our object storage, which had some credentials for the device. And when I entered the same code on the device, it picked it up and it issued the certificate to the device. Right. So now we have authentication set up. We have a communication layer. The messaging is set on the device. I can just give a name to the device. Let's say we call it ATO rover. I'm going to put some icon to it. And yeah, that's it. The machine is set up. You can see that it shows a green icon because it is online right now. Now, this shows the control panel for your machine. Right, so we already collect some basic metrics like the CPU utilization, the disk utilization, file system, system load, network in, network out, stuff like that. The agent logs also start coming on the cloud. So you can see that these are all the Mecha agent logs already available on the cloud. We have an explore button here. So if you click on the explore button, we launch a private tenant for your account's Grafana dashboard. So using the Grafana dashboard, you can actually consume the metrics and logs coming on the device on Grafana. Cool. The other concept is you can actually create networking. Now, one thing that we will quickly do is we're going to create an app service. The app service is the HTTP gateway that we just spoke of. So I'm just going to name it, let's say ATO rover. It is asking for a DNS name, so I'll just say atorover.app.mec.sh. Again, just to recap, this is in the similar lines as setting up a load balancer. It says, okay, the protocol is going to be HTTP. My target port will be 443, which is not, okay, it's a default, and the local port is going to be 4000. I'm going to write the 4000 port here, and I'm going to attach a machine to it. The machine should be, oops, 1 second. Okay. Yeah, so the ATO rover. Yeah, sorry, I just zoomed out a lot. Okay, so now you have an app service set up. Now I can just go to Postman. Now I will use a public endpoint, right, like a fully qualified domain. I'll just say ATO rover. And I'm just going to give the entire URL. This is the endpoint to actually move the rover further. Okay, it's a timeout error. Oops. Okay, so the first time it timed out. So yeah, so we are good. So that means, thank you. So now you have a remote control over the internet. From your office, from your home, you could manage your own robot. Yeah. So yeah, that's what the app service does. And yeah, free and open source software at Mecha. Some of our projects include the Mecha Make. These are build tools for you to build your bootloader, the kernel, and rootfs. The Mechanics GUI, it's our Wayland UI. Shell for touch-based devices, again in Rust. The MCTK is our canvas-based UI framework, which is running on OpenGL context. So this gives us like 60 FPS rendering on the device. The agent that is running on the device, which talks to our cloud, is fully open source. We actually want to open source our cloud services. We are trying to figure it out because it has a lot of moving parts. There is HashiCorp Vault involved. There is NATs involved, right? So our idea is that we may end up giving something called mini Mecha, right? That you can run on your local host or on your own cloud, which would be fully compatible with the agent. Meta Mecha, which is for people in embedded who like to work in Yocto and break their heads over it. If you meet somebody who says he does Yocto, you have to understand he pulls a lot of his hairs all the time. Yeah. Yeah, that's it. Thank you so much.